Okay, so now we have some simulated peptides, and we want to analyze them to see whether or not mutating this beta-hairpin has affected the folded state. So what I'm going to do now is bring in a script that will measure distances. So just use the source command to bring in a TCL file. I'll be sharing all of my configuration files and my scripts probably through GitHub. I'll put a link in the video. So I'm going to bring that in, and then in that script is a procedure called distance, and it is going to take some arguments. I'll show you in just 1 second. I do want to say I already have loaded this. This is the unmutated peptide in the water sphere, and I loaded the DCD file in the standard way on top of the PSF file. You can see it simulated. And so then just to show you this script file, I think I have another video on this, but since we're talking about it now, I'll open it up. And so it's going to take arguments here. So this is the procedure distance. Once you source this file that's also called distance, it's probably not the best way to do this. You shouldn't call your file the same thing as your procedure, but it's okay, it works. So I have a procedure called distance. It's going to take two selections. That in this case is going to be the ends of the peptide. I'm going to use the alpha carbons on the C and N terminus of the peptide. It takes a number that's N_D. That's how many bins you want to put into a histogram. It's going to go frame by frame through your DCD file, and it's going to save the distance between these two selections for every frame, and then it's going to create a histogram of those distances. So FR out is the actual distances, R for radial distance, and then D is a file name for the distribution of distances, so the subscript D is for distribution. And that's here in the top of the file, but that's what we're going to be entering here. So I need two selections, a number, and two file names. So I'm going to make the first selection. I'll put this in quotes. I think you can also use curly brackets. I'm going to use the first residue and the alpha carbon, and then I'm going to use the last residue, which is, I think it's 12. Let me just confirm. Well, I'm not going to be able to confirm that way, so let's look here. Just go to the end of the file and make sure that it is 12 because we removed this NH2. Okay, so come back here as ID 12 and C alpha. I'll do this with 50 bins. 50 to 100 tends to work pretty well. You can always rerun the script if you don't like the way things look. And then I'm going to call this distance C alpha .csv and histogram C alpha .csv. Okay, and then it will show me that it's going through frame by frame. 20,000 frames in this simulation, so it'll take a second to finish. I'm in the water sphere unmutated. And so it's going to create those files. It's still running. Sometimes when you have a lot of frames like this, it might look like it freezes. If you give it a second, it should complete. There we go. So then I'll just open that file to show you the contents. So here's the distance. And just to look at what's happening, I can make a graph of that. I think this is a good exercise for students to do. And you can see that the distance is fairly fixed throughout, somewhere around 5.25 angstrom. There are a few fluctuations where it appears that the peptide opens up to a larger end-to-end distance. And then I will show you the histogram. Looks like my Excel crashed. So the histogram, this is the bin for the distance, and this is the number of times that it sees those bins. I'll insert a graph of that as well. And you can see that you get a pretty sharply peaked distribution here of distance. I'm going to jump ahead. I have all of these files for several mutants, as well as the non-mutated version of the peptide. And so let me just show you then what that looks like and the way that I go through analyzing it. So I'll go to just the unmutated peptide here. And I've just brought in the histograms here. And so I have the histogram data for the unmutated peptide in vacuum. There's no solvent for this particular case. And I could plot these numbers here, but what I've done instead is I've calculated the probability. So I just calculate that as what is the number of times that this particular distance was observed, and divide it by the sum of all the observations, which was that 20,000 points. I would just add up the column B here to get that number. So I'm just adding up column B. Over, I put 100 points in this histogram. So this histogram has 100 points, and I'm summing up all the points in the histogram. That gives me this blue curve here, the unmutated peptide. And then I've also brought in a mutation of the second amino acid, tryptophan, to a glutamine, as well as the 11th, which is opposite to amino acid 2, or residue 2. 11 is on the opposite end. And so when we compare those, what we see is that in vacuum, the peptide tends to open up a little bit. The unmutated is just below 5 angstrom, and those two mutations both push the end-to-end distance out just slightly above 5 angstrom. In this graph to the right, I have the unsolvated in blue, and in orange I have the solvated in a water sphere. And you can see it appears that the normalization of these distributions isn't adding up because this distribution has a much smaller area under it. But what's happening is the points are spreading out quite a bit in the solvated one, so the distances are being sort of smeared out across a larger range, and so the difference between one point to the next is further apart along this distance axis. But these are both normalized, and you can see that solvating also opens up the end-to-end distance a bit compared to the unsolvated form. So you can make these comparisons. What does solvation do? And ask questions about why would solvating cause the peptide to open up. Other things you can do are to look at the solvated versions. And so here I've put all three of the solvated peptide together. And we'll expand this graph out a bit. And so in blue is the unmutated, orange is the second amino acid glutamine, and the green is the 11th amino acid mutated to an S. And what we see is that in this case, the opposite behavior happens. The mutation actually causes the native structure to close when it's solvated. But what we see are these extra distributions that are showing up out here at large openings. And you can actually see these in the distance file. If you look at the distances, you'll see these fluctuations away from this closed native structure to these large opening distances, and they're quite a bit more frequent than what you see in the what we saw in the unsolvated one just a moment ago. So let me just show you an example of that. So if I look at this distance file, you can see these much more long-lasting fluctuations away from the native folded state distance there. So that shows up very clearly in these distributions. My Excel really doesn't like these big files, apparently. Okay, so I'll just reopen this file that has all of the different mutations. And one last thing that we can do is we can take these probabilities and we can calculate a Gibbs free energy simply by multiplying the gas constant times the temperature of the simulation times the natural log of the probability. And there should be a minus sign. And so I'm going to take those two numbers and put those on a graph. And you'll get some strange things happening whenever there's not a number here. So for example, if I try and take the natural log of 0, I'm going to get something strange here. You can go through and remove all those zeros if you don't want to see those in your graph. But what you can see is that these probability distributions for distance can also be put in terms of a free energy. And so you can see then that for this, this is the unmutated peptide. You can see that there's a very large energy well that corresponds to the native structure. And then you can see that there are some energies that are further out with a larger end-to-end distance. I can do a similar calculation with one of the mutated ones. I can copy these numbers. them on this graph to see how that energy is changing. Let's just zoom in a little bit. We'll start at 4. And so then we can make comparisons about the free energy of this mutated structure, and we see that this unfolded state that's showing up here around 8 1/3, 8.5 angstrom in distance is starting to become comparable in energy, almost as low in energy as the energy of the folded structure. So these mutations seem to have a pretty large effect on the end-to-end distance of this peptide.